Um, Hello, everyone. Can you hear me okay? As Mark just pointed out, even the most complicated CAD algorithm cannot function well if the underlying item pool is of the pool quantity. So the presentation that will be talked about will provide a way to design item pool to start with to ensure that a CAD can function to its full potential. So my name is Wei He from NWEA, Portland, Oregon, US. This is a joint work with Mark Rakers. Um, Item pool design has become an independent research topic starting from the late 1990s. Um, Unlike the item pool assembly, which focus on assembling an item pool from the actual items according to the desirable item pool characteristics. In an item pool design effort, no actual items exist. The task is to generate an optimal item pool blueprint describing the distribution of items with all possible combinations of relevant statistical and non-statistical attributes. So in general, 3 key elements need to be focused in an item pool design effort. The first is to identify the item's optimal statistical features. The second is the item's non-statistical features as well as the item pool size. So far, there are 2 lines of approaches that have been developed to design item pool. The first is a mathematical approach represented by the well-known shadow test approach, short as STA. The other approach is more heuristic, represented by the Bin and Union method. This approach, also known as the P or R optimal method, which is specifically more applicable to the situation in which an item carries only one statistical attribute. To use the Bin and Union method in general, the following procedures need to be followed. First is to specify the CAD procedure. Then once the CAD procedure is specified, then administer the CAD to the examinees from the expected population. Then for each examinee, determine the ROP, or optimal pool, and then find the union of ROP. If the union of ROP is formed sequentially after each examinee is sampled, then the number of items will asymptote to the item pool size that we want to estimate. Here are some in-depth explanation of those key elements in item pool design. The first is to identify the item's optimal statistical feature. Now let's just use a simple case, which is the use of Roche model. As we all know, a Roche item can provide the best information when the difficulty and ability estimate exactly match with each other. So, for example, if we have an ability estimate of 0.13, then the optimal item difficulty value should also be 0.13. Now, let's see. At a certain stage of the CAT, we get an ability estimate of 0.3. Then we have 2 items. One has the ability of 0.13, and the other has the difficulty of 0.5. We calculate the item information for those two items. As we can see, the item information for those items are slightly different. However, the question that we can ask ourselves is whether those differences are, distinguishable. If no, what does that mean? Now, if the difference is not statistically significantly different, that means on the theta scale, we can on the theta scale, we can set up the beings with each being taking a range of values. Each being contains some items, and each being is mutually exclusive from each other. Now, if we administer a cat to an examinee, then we can just sort out those items with B values into different B being, and if we can, and as we all know, the items used for one examinee can be also used for another examinee. If we can take the union for each being and then summing up all items in each being, then we can basically estimate the item pool size. So this is an example of this is an example that indicates how the item pool size increases with the increase of the number of the similes. As you can tell, when the number of the similes is small, the increase of the item pool size really is significant. But as the number of the similes increase, let's say increase basic from starting from 7,000 all the way to 10,000, we don't see much difference in terms of its impact on the item pool size. Now, this is an example to show how the Bing and union method can be used to design item pool for two similes, which who have the chewability of 1 and 1.2. Now, the figure on the left panel depicts the item distribution for the first examinee with chewability of 0.1. As you can see, those numbers depicts the number of the items in each being. For the second simile, this is the distribution of items in each being. Now, if we look at this being with the range of 0.6 to 1, for the first examinee, the 6 items are sorted into this being. But for the second one, only 2 items. So if we take the union of the number of the items in each being, then rather than 40 items that are needed to that are administered to each examinee, we just need 34 items for those 2 examinees. Note the simulated cat has only 20 items. So this is the item pool, item distribution for the item pool designed for those 2 similes. As mentioned earlier, the Bing and union method is more applicable to the situation in which the item carries only one single non-statistical attribute. In the case in which task needs to take care of a complex set of non-statistical constraints, we need to figure out how to extend or use a Bing union and method and make it work. So this is an example of a more complex task blueprint. As you can tell, this task needs to take care of 18 constraints, and for each constraint, there's the weight and also low and upper bound that are associated with each constraint. So the research purpose of the study is threefold. The first is how can the Bing and union method be used or extended to develop item pools for severely constrained CAT. The second is, what are the desirable features of the item pool for the CAT, selecting items with multiple non-statistical constraints using the weighted deviation model, item selection method. The last one is, how do the item pools perform in comparison to the operational item pool. Now, specifically for the target CAT, this is the underlying CAT model. It used a 3PL IoT model. The ability estimation method is a combination between EAP and MLE. It used weighted deviation model for item selection. It's a fixed length task with 20 items, and no exposure control was considered. This is weighted deviation model. For the time's sake, I'm not going to elaborate on how the weighted deviation model works in terms of the item selection. But briefly speaking, the WDM, weighted deviation model, works in a way to select the items with the smallest weighted sum of deviation from the target value, both statistical and non-statistical. So, to extend the being a union method, there are 4 key elements that needs to be considered. One is how can we just design sort of a Bing map for the 3PL model? How to identify optimal statistical features of the 3PL items, how to identify the distribution of the non-statistical attributes, as well as how to model the weighted deviation item selection. Now, I'm going to talk about how we take care of those key elements one by one. Let's look at how we can design or develop a Bing map. Recall that in the Roche model case, the Bing map is kind of just one-dimensional. But for the 3PL case, we know that for the 2 or 3PL items, the item information actually has a lot to do with the magnitude of the item discrimination parameter. So that means when we design a Bing map, we have to look at not only the B parameter but also the A parameter. It's a combination of both. So for that, Lord's formula came to help. We know that the item's information is proportional to the quadratic function of the A parameter, if given by this formula. If we kind of slightly arrange this formula, we can end up getting this. And if we just substitute, you use maybe 0.2 or whatever, or 0.25 as C value, then we know that for A parameter, it always starts with 0. It's always a positive number. Then with this, given we know the amount of the change in item information, we can work out the boundary of the A value. So with this information, then we can design a sort of Bing map like this. So this is what we call AB Bing. So basically each block is a AB Bing, and items within this AB Bing are treated in equivalent in use. And we also have the B Bing, but in the 3PL case, the B Bing is a collection of several AB Bings. So this is another view of the Bing map. Then how to identify optimal statistical features? There are 3 ways that can help us do that. All of the 3 ways basically leverage the relationship between the item characteristics and the item information. So there are 3 ways: random approach, mixed which is basically just generate A and C out of the target distribution, and then use this formula given by Birbaum to calculate the optimal the B value. For mixed random and prediction approach, it kind of just leverage the known information from the existing item bank in terms of the correlation between the A and B parameter, and then leverage the also those the formulas to figure out the optimal items A and B values. The last method is called minimum test information. Basically, you have to specify the target test information and then break down those test information into item level. Now, how to identify non-statistical features? Now, basically, that's require a very close review of the test blueprint, trying to understand the relationship of those between those items, non-statistical attributes. So, specifically, to identify the item's non-statistical features, we need to do the following things. Recall that there are 3 attributes that needs to be taken care of by this test. So, for each item, generate a 1 by 18 vector, and then random pick up an attribute under some of the item major content category. And basically, this approach needs to, for each item, this approach needs to yield about 322 types of combinations of all the non-statistical attributes. And as we all know, for the CAT, when it comes to item selection, it actually looks for items within the whole pool. So that means, the item size that is identified by this approach may have some redundant items. So we need to, figure out some way to kind of trim down the item pool size. Now, for this specific study, there are 3 factors were manipulated, including expected amount of item information change, 0.2 and 0.4, the B being width, and item generation method. In total, there are 24 situations together. So I'm going to skip this procedure, how the simulation is done. If you are interested in the study, feel free to send me the email, and I'm happy to share the paper. We also use a couple criteria to evaluate the quantity of the candidate item pools. So those criteria include pool size, the ability estimation precision, the item pool usage, test security, classification accuracy rate, because the target CAT was a placement test, and as well as the constraint violation. So those are the results. Let's just quickly review the results. From this table, you can tell that the candidate item pool size is much smaller than that of the operational item. Also, both average A and B parameters for the candidate item pools are slightly higher than those of the operational item pool. We also found out that the B beam width and the expected item information change actually has some impacts on the item pool size. So those are those figures basically just compare the distribution of A and B parameters between the operational and the some of the candidate item pool. As you can tell, for the candidate item pools, the distribution of the B parameter are kind of more uniform. And this is item pool information. So this is operational item pool information, and those are the item pool information for some of the candidate item pools. As you can tell, the candidate items can provide better information at the the tails of the scale. And this is the distribution of the item attributes. So as you can tell, the biggest difference are here, attribute 3, 11, and 12. So those are the sort of the overall performance statistics. So in general, the candidate item pools actually perform much better than the operational item pool. And this is the classification accuracy. If you look at the last column, you can tell that all the candidate item pools can classify the stimulus much better into different performance categories. So in summary, compared with the operational item pools, all the candidate item pools yield better measurement accuracy and precision, provide higher correlation between true and estimated ability to estimate, better efficient item use, lower item overlap rate, lower constraint violation rate, and much higher classification accuracy rate. So the methodology that was discussed basically can function well in terms of generating item pools that can support the good functioning of the intended CAT. So how can those optimal features be used in practice? In general, there are two major areas which can benefit from the optimal item pool features. One is the item writing and development. So if we have the sort of desirable, and if we have actual, we can do some gap analysis to see what is missing, so that the item development can be focused on those gap areas. The other is that the desirable item pool features that are identified by the item pool effort can be used to guide the item pool assembly, which is a topic that was actually presented in several presentations yesterday afternoon. So this is the end. If you have any questions, feel free to email me. Thank you very much.
Good afternoon, everyone. So this presentation is about propose a new design for target content distribution for a variable length content balance CAT. So suppose we have a group of examinees. They're very happy to take the CAT. And for this CAT, it's a simulation. It means a simulated CAT, okay. And we have 6 different content areas. 1, 2, 3, 4, 5, 6. And for the first 2 content areas, it's a little bit easier. And for the next 2, 3 and 4, it's a little bit more difficult. So we can say it's medium level difficulty content areas. And the last 2 is more difficult. So we say it's like more harder content areas. So for the current CAT design in most studies, no matter which ability group the examinees are from, low, medium, or high ability group, the proportion of items being administered from each content area is the same. For example, I'm one candidate, okay? I'm from a little bit more, more competent group. And I would take number of 5 items from easy content areas and 10 items from difficult content areas. Then there is another examinee. So that examinee, however, is from a less competent ability group. But still, this examinee will be administered the same number of items from easy content areas and from difficult content areas. So given this situation, we're thinking about whether the CAT design for the content distribution can be a little bit different. I don't know how many of you have attended yesterday's presidential address by Dr. Markarakis. So his topic is about how adaptive can CAT be adapted. So given this situation, we're thinking about whether there could be a new design for the target content distribution for the cat. So instead of let all the examinees be administered the same number of items from difficulty and easy content areas, we proposed a different new design. So, okay. So here, still, we have 6 different content areas. The first 2 are easy content areas. The next 2 are a little bit medium difficulty content areas. And the last 2 are harder content areas. And for the current study, still, the proportion of items being assigned to all the examinees is the same for all content areas. But for our new design, suppose, for the lower ability group, we will increase the amount of items taken from easy content areas and decrease the amount of items taken from harder content areas. While for the high ability group, that's the opposite. We will decrease the number of items taken from easy content areas while increasing the amount of items taken from harder content areas. So basically, instead of the fixed target content distribution, so this design proposed a little bit adaptive content distribution, given different ability of groups. So this is the target content distribution for the low ability. You can see that these, examinees with less competent ability, they will be assigned more items for easy content areas, while less items from harder content areas. While for the examinees from a little bit more competent ability groups, they will be assigned more items from harder content areas, while less items from easy content areas. So based on this idea, we try to simulate 3 different pool designs. For example, we have 3,000 examinees randomly selected from a normal distribution. And the first pool we simulated is normal distribution pool, but for each content areas, the difficulty mean varies across all 6 content areas. So in this picture, you can tell that the blue shaded is the pool distribution, while the orange shaded is the examinee distribution. You can tell that the blue shaded is a little bit chubby and flatter. That's why we name it chubby pool. And the second pool we simulated is still normal distribution. However, this time, the content areas does not vary a lot across content areas, given the difficulty level. Instead, it's pretty similar. That's why you can tell that the distribution of the pool is very similar to the examinee distribution. That's why it's a little bit peak. So we name it skinny, because compared with the first one, it's a little bit, skinny and a peak. And the last pool we designed is the uniform distribution pool. So this pool is more flatter compared with the first 2 pools. So overall, we have 3 different pools: chubby, skinny, and uniform. So this is a closer look at the number of items for each content areas given the different difficulty beings. Because the way we simulated different pools, you can tell that for the skinny pool, for each different difficulty beings, the number of items for each content areas is evenly distributed compared with the other 2 pools. Okay, so here is the summary of the simulations. Overall, we have 3 different pools: chubby, skinny, and uniform. We have 2 different designs: new design and old design. And we have 3 different ability groups levels: low, medium, and high. And we have 6 content areas. And the test is variable length. The minimum is 6, and the maximum length is 250. And the following are the evaluation indices. So here is the result. So for this result, I don't show the result for each ability group because it's too many, but just the overall group. So you can tell that you don't find too many, a lot of differences, except that number of items being exposed, and overlap rate, and test length. And if you take a close look at them, for the skinny pool, it has, much different result than the other two pools. So, which is interesting to us. So we take a look at the test overlap rate, given the different three pool designs. So we have three pools: chubby, skinny, and uniform. So here is the overlap rates for all the examinees. You can find that for the new design, which is the yellow bars, overall it has lower test overlap rate. And for the skinny pool, it has much lower test overlap rate than the other two pools. And if we look at the lower bullet groups, the distribution of the test overlap rate is a little bit different. You can find that for the old designs, for the chubby pool, it has higher test overlap rate for the harder content areas. Then, if we look at the higher bullet groups, you can find that distribution also shifted a little bit. For the higher bullet groups, you can find that for the easy content areas, the old design, produced much higher test overlap rate. And the other thing we'll find that is for the skinny pool, for the lower bullet group, it has a little bit higher test overlap rate for the easy content areas. And for the higher bullet group, it has a little bit higher test overlap rate for the harder content areas, which is also very interesting. So this is the pictures I'm going to show you later about the items being exposed for the skinny pool. So for the new design, for the lower bullet groups, we can find that the number of items being exposed, given different exposure rate, is very different. It's interesting because you can see there are three lines here. So the bottom line indicating the exposure rate equal to 0.1. The second line is exposure rate equal to 0.2. And the highest line is exposure rate line for the 0.3. And you can tell that for the easier content areas, the new designs let more items being exposed for easy content areas. However, for the old design, you can tell that you don't see this pattern. Instead, the old design produced let more items being exposed for the harder content areas. And for the higher bullet group, still, for the new design, it let more items to be exposed for the harder content areas. And for the old design, you don't see this pattern. So this is the bars for the lower bullet group. It's showing the items administered by content areas for different difficulty beings for the skinny pool. You can find that for the new design actually has produced more items being administered for the content, for the easy content areas, for the less difficult items. While for the old design, you don't see this pattern. And for the higher bullet groups, still you can find that for the for the new designs, it produced it let more items being exposed for the harder content areas, for the difficulty beings. However, for the old design, you don't see this pattern. So here is the summary of the study. So overall, we can tell that the item pool usage has been improved, given different content areas by different difficulty beings for the new designs. And the new design let items being exposed a lot for those content areas that normally, for different groups that they don't select main items for those content areas. And if we compare the new design with old design, overall for the total bullet groups, you don't see many differences given the precision estimation. But for the pools that have content areas that varies, on different content areas for the difficulty levels, the new designs, definitely provide a little bit slightly better precision estimation for the low and high ability groups. And also, the new design, which is adaptive, content distribution, it provides like more items being exposed and lower test overlap rates for different content areas given different ability groups. So for the different pool designs, we can tell that the skinny pool definitely produced much better results given the precision estimation and the pool usage. So we would suggest that if you want to design a pool, we would recommend like adaptive content, target content distribution. And also we would recommend that the pool, item distribution in the pool, which will represent the distribution of the examinees distribution. So that's all for the study. Any questions?
Okay, Jingru's been so efficient in her use of her item pool that we have time for questions. So probably about 4 or 5 minutes. So if anybody has any questions. Must be that I was absolutely perfectly clear, or
excuse me. So do you think you're going to, I'm over here in the corner. Hello. Do you think you're going to get pushback from people who are used to saying we want so many % of items on the exam from each content area, and what would you respond to them?
So you mean like the people, they want a test blueprint, like force them to take?
Right, they want so many %, medical board exams, they want such % here, such % there, et cetera.
Yeah, that's a very good question, actually. When I was doing this study, I have this question in my mind too, but still, this is just like simulative study. We just want to show that whether we can let the content distribution be adapted based on the difficulty ability groups. So given your question, maybe for the extended study, we can try to see, maybe for those test print, they want, examinees to take particular items from each pool, what kind of adapted content distribution we can design to meet their needs, but also let those, adaptive quality for the CAT. Yeah. Thank you. Okay.
Do you assume unidimensionality of all the content areas? Because you do have to assume it, no? In order to just exchange content with difficulty.
Yeah, for this study, it's based on the Rush model. And I assume that's a unidimensional CAT.
This is the main problem, I think, in the whole idea, because usually when it's different content, it's not really unidimensional.
Mm-hmm.
And maybe you should have 3 tests for each one of the or 6 tests for each one of the contents.
Okay, thank you.
That's actually a really good question, but I bet we could survey people who have adaptive tests, and there's a lot of them who use a unidimensional model even though they do content balancing. So it's, it's kind of, so in one sense they're assuming a unidimensional model, in the other sense they say it's wrong because we have to content balance. So that's interesting.
When you have different item types, then it's easier to go this way.
Mm-hmm.
But when it's really different content, I wonder.
Yeah. Mm-hmm.
So you already answered the question about thinking about in terms of the proportions for when you have a blueprint, right? It's a bit easier, but I was wondering what your thoughts are in terms of the construction of the implementation of this would require that you have a target to which you're actually balancing, right? So if you have, if it's a traditional content balancing that's associated with a skill or a content domain, we know that we're balancing the item for the selection of purposes of meeting the actual blueprint purposes.
Mm-hmm.
So in a test, how would you inform a test maker, a test publisher, about how to actually choose their relative balancing of the difficulties, particularly since difficulty is a relative classification? depending of how you actually set the scale of your item pool, it was going to not necessarily be population invariant if you now have this whole balancing to a particular content difficulty for a group that will be taking a test. So how would you inform somebody to come up with the proportions for the balancing and difficulty?
Oh, that's a very good question, actually. I don't think I have the answer right now, but yeah, when I was, this is like a revised study about my internship with the NCLEX. So the first study, original study, is about to evaluate a real test pool, actually. And now it's just like different, it's based on a simulation study, so I simulated different pools, designs. Yeah, still I would think about this question, but I don't want to confuse other people's, right now, but thank you very much.
Maybe I'm repeating the same question as the previous questions, but with this kind of dramatic difference in content, it essentially expected to result in different test construct, and with different test construct like this much of a level of difference of content, maybe the meaning of a score across different construct no longer have the same meaning. So in other words, the score comparability can be threatened with this kind of different test construct. And maybe one of the way to make sure or evaluate the unidimensionality is that maybe we can design some experimental tests. Each test forms consisted only of each content.
Okay.
And see if and administer those experimental test forms to common groups of test takers, and see if they do show similar Sierra distribution. I'm just suggesting this idea. I don't know whether this kind of experimental design would be effective to evaluate unidimensionality, to make sure that the test construct consistent across all different test contents.
Yeah, that's a very good point. For this test, I just simulate as a licensed cat. So it's like it's like, either you pass or fail. Yeah, but yeah, I will consider about this later. Yeah, thank you very much. Yeah.
Okay, I think we need to move on to the last paper. And we will have time at the end for more questions and hope to stimulate more discussion as we get the full set of papers done.
Hi, everyone. My name is Qi Diao. This study was done by Xuechun and Mark. And unfortunately, as Mark said, Xuechun couldn't make it to this conference due to some issues with travel documents. So I'm going to present for them. And if you have questions, Mark is here. And if you have additional questions, please feel free to email Xuechun, and she'll be more than happy to respond. So the title of this study is Item Pool Design and Management Using P-Optimal Method for Mixed Format CAT. So why they want to focus their study under this specific topic? As many of the presentations in this conference have said before, that the quality of item pool is critical to the success of any CAT program. A very good example Mark gave in this symposium is, even though a student keep giving correct responses to the items, easier and easier items are given to the student. So we have from a CAT go to a BAT. So a CAT program cannot function as anticipated without an optimal pool providing informative items. And the definition of optimal item pool is defined here as one that can always provide informative items that satisfy the desired characteristics of a CAT program during implementation. And there are many item types, and for example, dichotomous and polytomous items. And a mixed format CAT program provides desirable psychometric properties by combining the threads of both item types. However, in the research literature, few studies have investigated optimal item pool characteristics for mixed format CAT. Therefore, the study focused their research on item pool design and management for mixed format CAT programs. So there are two research questions. For a CAT program consisting both dichotomous and polytomous items, given a modeled CAT, so what is the blueprint represent regards to the characteristics and the distribution of the items, item pool information, and pool size? So we want to simulate an optimal item pool and want to know the pool characteristics. And the second research question is, once we have this simulated optimal item pool, so what does it mean? The resulting item pool, what does it mean in terms of measurement precision and item pool utilization? So with those two research questions in mind, they designed the study. In this study, the method that you use is p-optimality method, which is the same as the bin and union method, just different terms. That is my understanding, as in Wei's presentation. So in the p-optimality method item pool design, given an accepted level of precision p, for example 0.9 here, an item providing 90% of the maximum item information is deemed equally informative, and items are thus described based on the ability interval bin. So basically, so here, this is the item information function, and the horizontal line is the 90% of the information. So any items that can provide equal or more than 90% of the information here are deemed to be equally informative. And from this horizontal line, if you go down to the theta scale, it equivalent to negative 0.3 to positive 0.3, then you will have your bin size for this particular one. And that is bin with 0.9 optimality. There's a neat feature of this bin design is the bin width can be set different depending on the test measurement precision requirement along the ability scale. So the bin width can be really flexible. It depends on where your decisions are. For example, if it's a classification test and the cutoff point, you probably want the test to be more precise. Therefore, you can set higher P, which means a smaller bin width for your interested point. But even if the CAT program doesn't care or care less, some of the part of the theta scale, for example, I don't care that much about the lower extreme of the ability range, then your bin width can be wider. So the resulting pool of smaller size with little loss of specified characteristics. So if you use the p equals to 1, which is 100% optimality, then you will probably end up with a very large item pool. However, using p optimality, the pool size can be significantly smaller, but with little loss of specified pool characteristics. So for dichotomous items, in this study, they generated informative items sequentially using the simulation based on the relationship between item information and ability estimates. And in this study, for dichotomous items, they used the Rush model. And informative item is the one with speed parameter equal to ability estimates. And in this study for the polytomous items, they use items with 3 response categories, partial credit model. And item information function depends on the order and the distance of step difficulty parameters. And items were generated based on operational item characteristics. So items are ordered step difficulty parameters and the distance between the difficult parameters are all less than 2.77, which give a neat feature of unimodal item information function. And the maximum locates at the middle of the two difficult parameters. So that is a large pool with 2,545 items with maximum information along the ability scale generated for simulation. So dichotomous items, the B parameters were generated during your simulation. But for the polytomous items, you first generate this large pool, and then during your simulation, select items from this pool. So this is the CAT simulation design. The last two columns, the first one is the operational program, which is comprised with multiple parallel fixed linear forms. And it has 3,789 dichotomous items and 116 polytomous items. So this is operational forms. And for the pool size of the simulation, which is the last column, it will be determined by the simulation using p-optimality design. And both use RASH and partial credit model. And for the item selection, as I said, for operational program, it's a fixed linear test, so there is no item selection algorithm apply here. And for the simulation, the initial item is from the middle bin, which gave a little bit random for the initial item selection. And the interim is the feature information. We also impose, they also impose item exposure control, and Rmax is set to be 0.2. And in terms of ability estimation for the operational fixed form, maximum likelihood estimation is used. And for the simulated CAT pool, they used variable step size until we observed both incorrect and correct responses in the response vector, and then MLE is used. And in terms of stopping rule, for the fixed form, it's 40 dichotomous items, and then 1 polytomous items. And then for simulated CAT, the stopping rule is variable test length. So you'll either reach information of 10, or you reach the maximum test length of 40 in terms of dichotomous items, and then you choose a polytomous item. So the simulation steps, they first randomly sample a simile from the expected ability distribution, and I generated items sequentially based on ability estimates. Next, they classify the resulting items into bin sets. And then repeat step 2 for next simile. Additional items were added only when there was inadequate number of items in the bin sets, or the existing items reaches the exposure rate. So the final optimal pool is the union of items in all bin sets after a specified number of similes. So in this study, what they use is 2,000 similes from a standard normal distribution to generate the simulated optimal pool, and then they replicate 100 times. So the result here is the average of the 100 replicates. And we can see from the first one is the pool size. For the simulated optimal pool, we only need 229 dichotomous items and 14 polytomous items. And then we look at the B distribution for the dichotomous items. And we can see the mean of the bin parameter pretty much comparable, but then the standard deviation of the simulated pool is larger than the operational pool, which means the B parameters in the simulated optimal pool is more spread out than in the operational pool. A similar thing happened to the polytomous items. And this is item pool information curves. The green ones are for the simulated pool, and the green ones are for the operational pool. And the first row of panel are for the dichotomous items, and the second row is for the polytomous items. So we can see, so this is pool information, and because the operational pool has many more items than the simulated pool, it doesn't make too much sense to see the absolute value of the pool information. But we can just look at it to see they pretty much have similar shapes, but the simulated pool is flatter than the operational pool, corresponds to what we saw in the previous slides, that is the B parameter is more spread out in the simulated pool. So now we have the simulated optimal pool. They use addition 2,000 simulees and take the test. And they want to see the measurement precision and the pool utilization. So in terms of measurement precision, the mean theta estimates is similar, and the standard error 0.3 is because we use information of 10 to be the termination criteria. And you can see in terms of correlation between theta hat and the true theta, the operational pool is higher than the simulated pool. And the operational pool, the RMSE is also smaller than the simulated pool. And in terms of classification accuracy, both in terms of correct classification percentage and in terms of false positive and a false negative, the operational pool outperform the simulated pool. But it isn't really the point. It isn't really fair to compare simulated pool to operational pool, because operational pool has a lot more items and is comprised with fixed linear forms. I think the point, my understanding is to look at the simulated optimal pool, and it behaves the way you anticipate it. And you can accept the performance of the simulated optimal pool. So now look at the pool utilization. The average path length for the simulated pool is 19, and operational pool is 17. And if you look at the percentage in terms of the number of items with exposure rates, simulated pool is much better than the operational pool, because the reason I just said, operational pool is so much larger and is comprised with parallel fixed forms. But I think more important point is that for the simulated pool, it behaves pretty well. So in conclusion, despite the large discrepancy in pool sizes, the summary statistics of the two pools show the following features. For both dichotomous and polytomous items, mean of the B parameter matches the target population. Items in the simulated pool are more spread out. Polytomous items in the simulated pool show larger distance between the two-step difficult parameters on average, indicating flatter information pattern. And the pool information function for both dichotomous and polytomous item displays similar shape. And although the operational pool performed better than the simulated pool with respect to correlation, RMSE, and classification accuracy, it is critical that the simulated pool performs as anticipated based on the evaluation criteria. And for the test efficiency, the average path length is similar between using simulated pool and operational pool. And due to the smaller size of the simulated pool, the item utilization is much better. An operational test is administered to a large number of examinees. The test blueprint derived from the simulation is helpful in subsetting the item pool for improving the security. I think this is one of the important findings is once you have this simulated optimal pool, you can do some diagnosis of your operational pool. And for security reason, you can divide your operational pool into smaller pools, mimicking the distribution of your optimal, simulated optimal pool, and you will rotate the smaller pool, so you can have better security. And then designing item pool not using an existing one delineates the pool characteristics as needed by a CAT program accurately. The resulting blueprint helps to manage an existing pool with respect to adding item needed, or I think this is should be redundant ones to improve measurement precision and test security. I think this is similar to what Wei says about doing pool diagnostic and gap analysis, etc. And the last is as item pool characteristics change with addition or retirement of items, the simulation can be conducted accordingly to update the blueprint. Yeah, that's it. Thank you.
I didn't even have to show my 5-minute thing because you were going to be done anyway within time. So you did a wonderful job. So you did a wonderful job considering that you have to come in and help out and present the paper. So it's kind of thank you. Questions? And we have plenty of time for questions for any of the presentations. If you have, everybody was very efficient in their use of time, so we have plenty of time for questions.
Yeah, for the first presentation, I was really intrigued by the idea of an item pool utilization index. I mean, that sounds like a very neat idea to me. Now, it struck me that the implicit ideal is to have a uniform information distribution across the scale for the pool. And I wonder how realistic that is. I mean, for the 2PL model, it's a well-known fact, and nobody knows why, that the A and B parameters always correlate. It's not a statistical artifact, but nobody knows why. That means that at the upper end of the scale, the information is always higher than at the lower end of the scale. So, and that means that your utilization index is always lower at the higher end of the scale, because Imax is higher at the higher end of the scale. So that's one effect. The other effect is guessing parameters. At the lower end of the scale is guessing, so there's always less information, which means that your utilization index goes up there. I wonder if you have any thoughts about this, but
yes, I should let Emery answer that question. But since he's not here, I'll give it I think it's a good point, because in doing the work, when you go into the 2 and 3 parameter model, things become much more complicated. And I could see at least, and I think your points are well taken. Now, me doing this, and I don't know this was how he would answer it, but the way that I'm answering it, is that I could see that you could, instead of having a fixed value that you're using for Imax, that you can have the value of Imax be a function of the level of theta on the scale, and use this variable level of Imax to go over and use this for the index, reflecting the reality of what you actually see with real item pools. And I'll suggest this to him as future research. He can go over and see if he can generalize the procedure to have a variable value of Imax that's in there. And I think he's actually already been thinking about that kind of problem. But I think it's a really good point. They are correlated, and you never do have the same information at the bottom end as you do at the top end of the scale. So it's a useful thing to do.
thank you. Yep.
Okay. Any other questions? If there aren't any, I'm going to make just 2 summary comments about the session, because this is my way of having a soapbox to go over and push something. Let's see if this mic is still on. The function of this symposium, the reason we wanted to have it is 2 reasons. One is to try and emphasize more the idea of the design of item pools prior to the development of items. To think about what you want your item pools to look like before, because in the past, too many item pools were developed by, well, we had paper and pencil forms, we calibrate them, we put them on the same scale, and you use that 6 or 7 or 8 paper and pencil forms and create an item pool from it, but it's not been optimized for the use with a CAT. So this is one motivation for it. The Emery's paper is another piece of that, and that is to, if you have a pool already and you want to evaluate it, this is a way that you can go and evaluate it and find out if there are places where there's weaknesses for it. And it's a newer thing. He's just started working on this. It's a newer idea, but it's a way of diagnosing the item pool that you have to go over and see if in the future you might want to go over and change the way the item pool is designed. So, but the overall theme of this whole session is, let's think more about item pool design, because the procedures aren't going to work very well if you don't have item pools that are designed to go over and support them. So with that, what I'll do is, if there are any more questions, we can answer them. But I want to thank my colleagues for, first of all, me for stepping in for Emery, Chief for stepping in, and and everybody agreeing to go over and do this. So I'm really pleased that everybody was here, and thanks for coming. Any other questions? One more. Here we go.
So one challenge I have, in the past generating items is that, you're aiming for a certain level of difficulty, and often the result is far off. So I just wonder, it's nice in theory to say I want, 12 items to have 3 difficulty or whatever, but in reality, you don't have so much control over that. So I wonder whether, that's just me being bad at generating items, and if so, how we can do it a bit better.
Well, see, I don't know who the question's for, but do you know who you want to answer it? Or I'll answer it. Well, one thing, we actually did this as when I got started into this area, we did this kind of analysis for the NCLEX exam that we've been talking about I talked about it yesterday and today. And initially, the NCLEX exam had an item pool that they used that had 2,000 items that they had developed, and it worked well with 2,000 items. But we went through this kind of analysis, and we actually found out that you could do equally well with 1,600 items instead of 2,000 and have no loss in precision, and you could actually get better use of the set of items that were there, and everything would work really well. And it also had a different distribution of the items because it changed the spread of the items in the sense of the way that it was done. And that became a target for item development. So it's not necessarily that you're going to go over and run into a situation where you're going to have to go over and produce more items or something. It's an ideal that can't be achieved. You might actually find out that your operational item pool is maybe overweighted in certain areas and underweighted in others. And if you change the distribution somewhat, you might get the thing to work more effectively and more efficiently, and you might actually save some money and not have to develop as many items. But you won't know until you actually go and look. So it's and it does force you to go over and think about what you really want the test to do, because in this NCLEX exam, it's really a decision-making thing for pass-fail, and so you need a lot of items near the decision point, and less items out at the extremes, and so that's the way the item pool gets designed to go. But it does have exposure control, it does have content balancing, and you have to deal with all these things when you're developing that item pool. But you can still go and do all those things, and in the case that we looked at, we actually reduced the pool size by going and doing this kind of analysis from what they had been doing before, which they had sort of developed through experience, thinking, well, they need around 2,000. That's because that maximum test length on their test is 250 items. That's why it needs such a huge pool. But we got it down to 1,600 by doing the analysis. So we saved them 400 items. So they were happy. So.
I want to add to what Mark mentioned a little bit. I think I kind of understand the pain that, I want the item maybe was difficulty of 0.1, but in reality, how can I just, ask the item writers to write an item with that specific item difficulty? From our experience, we actually, very experienced item writer actually can do that. In a company that I work with, we do ask them to try to develop items with certain difficulty, and most of them actually do a pretty good job. We actually look at the correlation between the sort of, educated guess of the item difficulty and the item final calibration. The correlation is pretty high. It's about, between 0.7 and 0.8. So definitely, I think, the information that we can get out of the item pool design actually can be used to benefit item writing and item development. I hope that helps.
Again, you assume that to steal 600 items is the same like stealing 2,000 items. And if you do the subsets, then it solves the problem, because then you randomly select one of the sub pools and you use one of them, and then you really make use of all the 2,000 items, which is a good solution. But if you just compare them, this is good for simulation, but in the operational world, well, items are stolen.
All right, and you can go over and model well, we actually have modeled, let's say, item disclosure, and looked at part of that in developing the item pool design. To go over and make some certain kinds of assumptions about the likelihood of items being stolen or released or accidentally, whatever, and looked for ways to go over and model that, and then so that you could use that as part of your item pool design. And then likewise, you can also use that in terms of refreshing item pools, about when, what kind of indicators you can use to say, well, this item is shifted in difficulty, and so this likely means that this item is now out on the internet someplace and we should get rid of it because it's not around anymore. We now have to replenish the pool to go through it. So I think that is a really valid point. When we did the thing for the NCLEX, we actually did do the development for each of the content areas separately when we were doing pool size, because they had different weights for different, and this is for a nursing exam, and they kind of wanted different amounts of items in different areas within nursing, and so we actually developed, in their case, separate pools for each one of those, and developed the design for that, and then put it together to make the overall pool. Which brings up another question on Jing Ru's thing. I understand for certification licensure that this is a problem. If you're going to certify somebody, you want to make sure that they know all the different content areas. So, but in the school context, when you have an adaptive test, I'm always really bothered about the idea that here I'm having a student who's having trouble with easy arithmetic items, but my content specification says that they have to take those hard algebra items anyway because that's what the content spec says, in order to content balance. And it seems like torturing this poor student who's over here and having trouble with the easy things, but you force them to take the hard things because that's what, the content people said they wanted them to take. So it depends upon the context of where you're working. If you're working on making a decision about competency for a particular profession, that's one thing. If you're working on one of these tests, which I was in the earlier session there where they're looking at growth of student performance over years and things, it sometimes doesn't make sense to go over force your same distribution of content at all levels of ability because somebody said that they should, so that's sort of a different kind of situation. Okay, any other questions? Now we'll let people all relax before having dinner, and kind of, and then I'll just say thank you all for coming, really appreciate it, and thank you for all the questions.